Hi, everyone. Thank you for connecting to my talk. Today, I want to share the joint work that we developed at the Singapore University of Technology and Design with the University of California, Santa Cruz and UpGate. The work is called AttkFinder, Discovering Attack Vectors in PLC Programs Using Information Flow Analysis. First, I want to present what is industrial control systems. For those who are not familiar with this type of systems, so industrial control systems are computing systems that manage critical physical processes like manufacturing plants, power plants, water treatment systems, public transportation infrastructures. Those systems are very critical for modern societies because societies rely that those systems run all the time smoothly. So you want that when you turn on a light, the energy comes to your house or your office. And also, for example, hospitals and critical buildings, they also rely that those systems are always available. So in the previous 10 years, we have heard about different cyber threats that have affected this ICS. So the first one is Stuxnet. I think most of us are familiar with this. So Stuxnet was the first cyber weapon that affect industrial control systems, at least as far as we know, and it affected uranium enrichment plant in the Middle East in 2010. Then we have the incident with black energy that it affects the power system of an Ukrainian town during the Christmas on 2015 and 2016. We also have the Triton malware that was affect natural gas system in 2017. Most recently, we heard about the Colonial pipeline. This one is a bit different than the other three because attackers didn't want to affect directly the physical processes, but it was like a side effect of the general attack. What all these attacks, or what of these cyber threats have in common is that the attack vector that the attacker used was a network based. So basically from the network, the attacker or the malware was able to affect the physical properties of the system. And that's something that we want to explore in this work. So first, let's start with the ICS communication. So this is a diagram of how this type of systems work. So the computing power of these systems are based on industrial computers, which have very particular features. So those industrial computers are called PLC, Programmable Logic Controllers, and they receive signals from the sensors. So the sensors are connected to the physical process. So the sensors are reading the physical properties of the system, of the process that you want to control. Then those signals are delivered to the computer, to the PLC. Then the PLC runs some programs and delivers some signals to the actuators, which manipulate the physical properties of the system. Usually, those type of ICS, they have something called human-machine interfaces, which are some special computers where the operators of those systems can control or can manually deliver also control signals. Or the operators can supervise how the process is running from these particular computers. So the communication, the ICS communication has some special features in comparison with the classical IT systems. So for example, HMI systems monitors and control actions at the PLCs. The messages that that travels from HMIs to PLCs travel in plain text. So there are not any encryption mechanism on this network. HMI or any other device that is in this level of the network can query information from the PLC. So basically, the state of the PLC is visible from any device that is connected to this network. The way how the PLCs are configured are also very particular because of the way how they work. So by default, all the variables that are configured on the PLCs are read and write, has read and write privileges from any other device in the network, because the idea is that they want the engineers want that the system is open to any device that wants to connect to them. And there is the PLC has a very special feature called a scan cycle that governs the way how the program that is configured or is coded into the PLC behaves. So here we see a diagram of the scan cycle. So the scan cycle can be seen as a loop that makes infinite loop that makes that the program that is running in the PLC runs continuously with in this cycle. So there are 5 main steps that the PLC takes. So first, the PLC takes the readings from the sensors. So they have a special buffer for that. So those readings from the sensor are stored in that particular input buffer. Then the network communications also has a different buffer. So all the messages that comes from the network are stored in this particular buffer. Then the third step is the control logic, which is the program that runs on the PLC, evaluates the state of those particular variables at the buffers and runs the control logic. The state of the output of this program are updated into the output buffer, and those signals go to the actuators. And then the 5th step is a safety checker, just to check that everything in the PLC is running okay, like all like power and memory consumption are in the standards. And then the 6th step is the scan cycle repeats. So it repeats again the same steps. Okay, let's see what is the threat model that we consider in this particular work. So in our threat model, we assume that the attacker can sit in the network. So we don't discuss how the attacker can compromise the network. We just assume that in some way the attacker is already in the network. And then from the network, the attacker has certain numbers of capabilities. So for example, the attacker can intercept network messages that travel between PLCs or among HMI, PLCs, and other devices. We assume that the attacker can query data from the PLCs, as I already described. We assume that the attacker can get access to the PLC code in some way. So that could be even if the attacker intercepts code when the code is being uploaded to the PLC, or maybe also the attacker can compromise some laptop, some workstation that is connected to the network and has the source code of the PLC. The attacker has some limitations, like the attacker cannot update the PLC code. And the goal of the attacker is that he or she wants to influence the actuator signals. Why? Because if it manipulates the signals, he can change what the physical process can do. He can affect the physical process, which is the final goal of the attacker. So given that those capabilities, what the attacker can discover diverse attack vectors. So the attacker wants to have like a very diverse set of attack vectors to compromise the whole system, and that's what AttkFinder tried to do. So we proposed this tool set called AttkFinder. So basically what it does, it takes the source code of the PLC in different languages. So the control logic can be written in different programming languages that are standard for PLCs. So like ladder logic, structured text, function block diagrams. And so AttkFinder takes the PLC code written in these native languages, and then it creates some graphs. It does some static analysis to create some graphs. Then it runs information flow analysis to deduce some information that some features that we call it attack tactics to build attack vectors. So there are some challenges associated with this approach. So first, doing a static analysis of PLC programs is different from the normal program languages. So one of the challenges that we have is that building the graphs, and also develop an engine to perform simple execution of PLC programs. Also, in our analysis, we include the concept of scan cycles, which is not typical in the classical IT, in the classical computer science. So yeah, we include this feature of scan cycles to run, to see what are the consequences of what are the interdependencies in the program in many scan cycles. Then we also evaluate different data structures that these particular PLC programs have, like, for example, timers, which are like very special features for PLCs. So those are the challenges that that we had to face to develop the AttkFinder tool. Okay, I will start with the running example to describe how AttkFinder works, and then I will proceed with a more realistic scenario. So first we have this tank. So this tank has two different actuators, a motor valve and a pump. The motor valve is feeding water into the tank, and the pump is leaking the water out of the tank. Then we have two PLCs. PLC 1 controls directly the tank, so it turns on the motor valve and turns off the pump. And the PLC 2 is delivering messages to PLC 1 according with when the operator or the system requires that the water is provided to the next phase, say. So in the diagram in the center, we see the PLC code of the PLC 1. So basically what it does is first it reads the sensor and the messages, then it evaluates what is the level of the tank, and depending on the level of the tank, it will turn off the motor valve or turn on the motor valve. So if the level is too low, below the low sign, it will turn on the motor valve to feed water into the tank. So the idea is to PLC 1 should guarantee that there is always water in the tank. So the water should be between level H and level L. And then it will provide water based on the network message that receives from the PLC2, which is the D variable here. We also use the system model. So this is a hybrid system model, how the whole system works. So this particular hybrid system is a hybrid automaton. So it has 4 different locations. So one is for when the water is going down in the tank, and the other is when the tank is feeding, the water level goes up because the motor valve is feeding water into the tank. And the other 2, location 2 and location 4, are transition locations. So after running the static analysis, we got 2 different graphs. So one is the control flow graph of the system. So we have 5 different blocks, B1 to B5, and the different control flows that the execution of the program can take. And then we have a information flow data graph, sorry. And this graph shows how the variables are related. So it shows, for example, the variable MV can take the value on or off in lines 8 and 9 of the code. And also, for example, when the variable P can take the value off in line 9, or can take the value given by the D message in line 6 and line 11. Okay, given all this information, AttkFinder will try to get some ways to attack this particular system. So we have the attacker goal is how to turn on the actuator P. So first, the attacker will use the information flow data graph to find the definitions of P. So for example, in this case, definition of P are in line 6, line 9, and line 11. Then it will identify what are the possible blocks that he wants to affect. So the blocks are block 2, block 3, and block 4. Through symbolic execution, it will produce some symbolic statements based on these particular blocks. So those are the path conditions that the programs need to satisfy to reach those particular blocks. So then it checks satisfiability based on what they want to do. So for example, in this case, they want to turn the pump on. So the path condition 2 and path condition 4 are valid, while path condition 3 is invalid. So the attacker can take path 2 or path 4 to make the attacker possible. Then it will produce concrete examples or concrete values of these particular symbolic expressions. Those are what we call attack tactics. So basically, those are the building blocks to build the attack vectors. We also introduced the concept of effort index, which is the number of variables that the attacker needs to manipulate in order to make an attack tactic valid. So our assumption is that if the attacker needs to manipulate more variables, that will be more challenging for the attacker. Okay, then we will we test this in this tool in a realistic scenario. So we use one of the test beds that we have at SUTD. So we use the two first phases of this particular testbed. This is a chemical dosing system. So it's two tanks connected, and when the water flows in this pipe, the system just feed the water with some particular chemicals to make it drinkable. So we have the connection diagram, how these two PLCs are connected, and how are they connected to the HMI and the different sensors and actuators that they have access. So in this scenario, we have two attacker profiles. One has access to only network messages, and the other is more powerful and has access also to, he can read and write messages to the PLC. So basically he can manipulate the variables in the PLCs. After running AttkFinder, we found different number of attack tactics with a different effort index. So those are listed in all actuators with different levels of complexity. So similarly, like the example that I explained earlier, so we have this system is a bit more complex. So this is the diagram of this is the system model for the first PLC. So these have 8 different locations, and for different combinations of the behavior of the tank. So in this scenario, let's say that the attacker wants to overflow the tank 1 of the L11. So first he will identify in the system model what is the location that he needs to reach. So to overflow the tank, the locations who are the nearest are location 14 and 13. So the idea is to keep the system in these particular locations. Why? Because in those locations, the motor valve is always on. So that will make that the tank overflows. So to stay in that particular locations, we need to keep the level, at least the sensor ratings, less than 1000 for this particular scenario. Then after running the AttkFinder, we will get different attack tactics. So 2 attack vectors that use different attack tactics. So the first attack vector use attack tactic 2, and the second attack vector use a combination of attack tactic 1 and 3. In our paper, we describe different types of attack vectors that we discovered using a different combination of attack tactics. So we demonstrate tank underflow, pump deadhead, pump dry run, and component denial of service, which is like using different signals or manipulating signals that comes from actuators. You can make that the PLC thinks that the actuators are broken and then like locked the actuators. And also we perform some chemical contamination attacks. As a conclusion, okay, further details can be seen in the paper. So those who are interested can have a look to our work. So as conclusion, we in this work we present the introduction of the concept of attack tactics that can be used to build attack vectors that will make the system perform out of context behaviors and will affect the system. We develop an information flow guided symbolic execution engine for PLC programs. And we show how using attack tactics, we can compose attack vectors to perform different type of attacks in industrial control systems. Thank you very much for your time. I'm open to questions. If you have any further questions, you can reach me at this email. Thanks for your attention.